So let's start recording. So today we are on our fourth lecture of this wonderful semester so far, and we have been working on simulation. So let's load up our second packet on our second PDF on simulation. Let's remind ourselves or everyone that we will have a quiz on chapter 1 and only chapter 1 next week on Thursday, a week from today. The solutions to the chapter 1 homework will be posted early next week. I want to give you the opportunity to work on them before you see the solutions. And then you have the solutions so you can see the answers and compare it to what you got. And then on Thursday, did I say the quiz should be Thursday or Tuesday last time? Tuesday, right? Tuesday, my apologies. Then on Tuesday, the quiz is Tuesday. Let's make sure we have that down. We'll start by answering any lingering questions, or just one or two lingering questions, go into the quiz, and then continue. So we were on simulation, and I know we covered, we were on the kindergartner class, I believe. And we did the situation where you flip 15 coins. And after the 15 flips, you'll have a certain number of heads. Let's remind ourselves what's going on, right? You're teaching a kindergartner class, and you're curious how many boys and girls you're going to have in that class. So you flip a coin 15 times, and you denote heads to be boy and tails to be girl. And if you get, for example, 8 heads, we say, okay, so that class had 8 boys in it. And then you do it again, another 15 flips. And this time when you do 15 flips, you get 7 heads. So this class has 7 boys. And then you do it again, another 15 flips. This one got 11 heads. So this is 11 boys. And you do this 1,000 times. And every time you flip the 15 coins, every one of those 1,000 times, you're flipping the coin 15 times. So that's 15,000 flips in total. And each 15 flips denotes one class and gives you a number between 0 and 15. And after you do 1,000 times, you'll have a bunch of zeros, a bunch of ones, a bunch of twos, a bunch of threes, fours, 5, 6, all the way to 15. If we look on slide 6, so slide 6 is an actual simulation where they did this 1,000 times. And as you can see, on the horizontal axis are all the possible outcomes, 0 through 15. That's the horizontal axis. The vertical axis is the frequency. That's how often each of them occurred. So according to this simulation, out of the 1,000 times that we did it, how many times did it end up being that we had 0 boys in the class? 0 boys, not 1 boy, but 0 boys.
0 out of 1,000?
0 times, right? 0, if you look above 0, all the way to the top, the number 0 tells you that not one time did you have 15 boys straight up. Not a single time out of that 1,000. How many times out of that 1,000 did we have 2 boys?
2 out of 1,000.
It occurred twice. And how many times did we, sorry that again? I meant 1 boy. How many times out of that 1,000 times did we have 1 boy? Twice.
1. Oh,
twice, right? There's a 2. How many times did we have 2 boys?
3?
Well, look at what it says. What's the number above 2? 5, right? That occurred 5 times. So every number above the columns is just a summary, because it's kind of hard to read from just the columns exactly what the number is. Is that 205? Is that 206? I can't tell. Well, let's just write it on top. That way you don't have to guess. So if I add up all the numbers on top, if I add them all up, 0 plus 2 plus 5 plus 11 plus whatever, what does that have to equal to? 1,000. Exactly. That's 1,000. Those are all the possible situations and how many times each one occurred out of the 1,000 situations. If I now say, what is the probability of having 0 heads or 0 boys? If I say, based upon my simulation, what is the likelihood that I have 0 boys? What would I say?
0%.
0% or 0 out of 1,000, correct?
Yes.
And if I say, what's the probability of having, let's say, 7 boys? That would be what?
7%.
Well, forget about
200
percent. Just give me the fraction, huh?
206 out of 1,000.
206 out of 1,000, which, by the way, is a little over 20%. Because how many times did I have 7 boys? 206 times. How many runs were there? 1,000. So what is my empirical probability? 206 over 1,000. What is the most likely number of boys based upon my simulation?
207.
207.
So not 207. I'm not going to have 207 boys in my class.
8.
Okay, so the answer is 8, right? The most likely number of boys that I can possibly have is 8 based upon my simulation, because that's the highest probability. That's 207 out of 1,000, correct?
Yes.
And what is the least likely number of boys that I have?
0.
0 or
1.
15.
or you can't have 20 boys. That's impossible in a 15-kid class. That would be
15?
amazing. But
Oh,
0 or 15, correct? So those are very unlikely. And if I did have 15 boys in the class, if I come to class the first day and magically I have 15 boys, I would probably look for an explanation, because from a purely statistical or probabilistic standpoint, it shouldn't happen. It's so unlikely to have 15 boys. And if I actually did have 15 boys, I might say something along the lines of, wait a second, this doesn't make sense. What's a good explanation for how I can come to class and have 15 out of 15 boys?
They shipped all the problematic kids in your class.
Wow. Wow.
It's not
Wait.
boys.
Whoa, hold on.
It won't be
Hold
the
on.
first time.
Let's read between the lines there. Wow. Okay. You know, just so you know, girls can be problematic too, okay?
I'm not saying that we can't be. I'm just saying.
Jeez, that's crazy talk. Okay, but that wasn't what I was going for. Give me a better one.
An all boys school maybe?
That came out really, the way it sounded was a long, drawn out, difficult to hear answer. So can we try that again? Hopefully it'll work. What's a good explanation for why? Or you can type it in. An all boys school, right? I show up and it's, oh my God, all boys. How's that possible? Well, dude, you just got hired at an all boys school. That's how it's possible. It's like, oh, okay, well, that kind of makes sense then. So if you end up with something that probabilistically is very unlikely, you got to start looking for explanations. Here's another one. Forget about math for a second. Suppose you won the lottery 5 times in a row. Suppose you buy a lottery ticket, you win $100 million. You buy the next one, you win a crazy amount. The next one, suppose you win 5 times in a row, which is so unlikely of an occurrence. But suppose it happens. What happens next, realistically, here on Earth? What is a realistic next scenario if you win 5 lotteries in a row?
You get investigated.
You get investigated. It's such an unlikely occurrence that it can't happen. It's fraud, you hacked it, you did something. But you get investigated because an unlikely occurrence actually happened. It's just that the world does not work that way. So if I actually got 15 boys, which according to my simulation is so improbable of an occurrence that it should essentially never happen, I look for another explanation. Does that make sense? Okay, now if I got 6 or 7 or 8, okay, that's fine. So let's look at question E. It says, what do the numbers in the lower horizontal axis represent? The numbers in the lower horizontal axis represent the possible outcomes. I can get 0 or 1 or 2 all the way to 15, right? Those are my possible outcomes, correct? Then it says, what about those along the top? What do the numbers along the top represent?
The actual numbers?
The actual numbers, what do you mean by that? There's numbers in the bottom too. 0 through 15 are actual.
Well, they're not the simulation. They're the, isn't it the actual numbers?
Well, but when you say the actual numbers, I have to ask what you mean, because 0 through 15 are also actual numbers.
Would
So-
it be the number of boys total from the 1,000?
Well, remember, the 1,000 is not how many boys there are. The
I mean,
1,000 is how many
total
classes there are.
students.
Huh?
1,000 runs in the
1,000 run.
Right. So I'm asking, what are each of those numbers on top? What do each of those numbers represent? When I look at the number for
The boys and girls.
not
The
exactly.
boys.
Flips of the
No.
coin, whether it was head or tail out of 1,000.
I understand. So again, let's look above 6. Above 6, we see what number?
141.
141. What does that number 141 represent in this case?
Boys.
No, you can't have
And
boys. The boys are 0 to 15. 141 is not boys. There's either 0 boys, 1 boy, 2 boys to 15 boys.
The number of times when you flipped the coin, it occurred that you got boys. That number of boys.
Yes, that's it. 141 times I got 6 boys. That's the number of times that I ended up with 6 heads or 6 boys. Remember, I did 1,000 flips, not 1,000 flips. I did 1,000 runs, correct? Each run ends with a number between 0 and 15, and that number represents how many boys were in that class. So out of the 1,000 classes that I looked at, out of my 1,000 simulations, 141 of them had 6 boys in it. And that's what the 141 represents. Does that make sense?
Yes.
So, F, use the dot plot. And by the way, even though those lines in the graph look like they're full, they're actually dots. Every time we got a number, we make a dot, and then we count the dots. But there's so many dots that they kind of clump together and it looks like a straight line. But it is still called a dot plot. So use the dot plot to estimate the probability of getting exactly 4 boys. What's the probability, of, according to my simulation, of getting exactly 4 boys?
Landing on 1 time.
75%.
Give me a fraction.
70. Oh,
Give me a fraction.
51
1
out of 1,000.
51 out of 1,000.
how did you get that? Sorry.
Because it happened 51 times.
Oh.
Right? It
Oh,
happened,
because you look up. Okay.
you look on top.
number
It
of
happened
times.
51 times, right?
So just so I can put it on my notes, the numbers on top are the times that it happened out of 1,000.
That's correct. That's exactly what it is. The number on top is the number of times it happened out of 1,000. That's exactly what it is. Okay?
What's the label for the bottom? Sorry.
The label for the bottom is boys or heads.
Kids.
I mean heads
Heads or boys.
are simulating boys, right? So if I
Got
get 12 heads, that means I had 12 boys.
That was
Simulating.
possible outcomes, but
Sorry?
I thought it was possible outcomes.
Yeah, but what are the outcomes here? The outcomes are how
Heads
many
or
boys we
tails.
have, right?
Boys.
See, David, the point is that the outcomes is generic. Boys is in context of this problem. Does that make sense?
Yes.
Okay, so what's the probability, according to my simulation, this is the second half of F, of getting 4 boys or fewer? How would I do that, getting 4 boys or fewer?
Would you just add 51, 11, 5, 2, and then all that out of 1,000?
That's exactly it.
1,000?
That's exactly it. Right?
Can
You
you
look
just
at
repeat that?
you look at all possible ways of getting it, 4 or fewer, that's getting 0 or 1 or 2 or 3 or 4 boys. And then you have to count, well, how many of those 1,000 times did I get? 0, 1, 2, 3, or 4 boys. So you look at those 5 numbers on top, you have 0 plus 2 plus 5 plus 11 plus 51. And then you divide that, whatever number that is, you divide by 1,000, and that's your answer.
Now, can I ask this? At the other end of the graph, you have 5 and 1 as well. So do you
Right,
add
but-
those 2 as well?
No, because that 5 is 13,
Ah, gotcha.
right? And that
That's-
1
oh,
is
that's right.
14 boys,
13 boys.
right? It's how many times the 13 boys occurred. Yes, Miriam.
So you're saying the 5 on the left and the 5 on the right is the same 5. You don't need to add that twice.
Well, it's the same 5 in terms of the numerical value, but they're representing 2 different things. The one on the left says, I got 2 heads 5 times.
Yes.
The one on the right is saying, I got 13 heads 5 times.
So we do add 5 plus 5.
No,
Wait,
because we want 4 or fewer, right?
Yes.
So we only look at 4 heads, 3 heads, 2 heads, 1 heads, and 0 heads.
Okay, I see.
And the numbers on top of 4, 3, 2, 1, and 0 are just the 5 numbers on the left. We don't look at anything else.
Okay.
Does that make sense?
Yes.
Okay. So let's look at the next slide. It's the same dot plot. We're continuing with the same situation. And what we want to do now is we want to make a probability distribution table. Let's remind ourselves what a probability distribution table is. It's a listing of all possible outcomes. That's the first column. And the second column is their corresponding probabilities, correct?
Yes.
So what are all the possible outcomes for how many boys our class is going to have?
0 through 15.
It's still
0 to
0.
15.
It's still 0 through 15. So the first column is going to be 0, 1, 2, 3, 4, all the way to 15. And then what's the second column going to be? This is something we just did. We just did on the previous slide. What is the probability of having 0 boys?
Whatever number out of 1,000.
Whatever number out of 1,000. So 0 out of 1,000, 2 out of 1,000, 5 out of 1,000, 11 out of 1,000, whatever those numbers were, that's going to be what is directly to the right of it.
The top numbers on the chart, right?
The-
Over 1,000.
Oh, yes, the top numbers in the chart over 1,000, correct.
So if we're saying one boy will be 2 over 1,000, right?
The likelihood of having one boy is 2 over 1,000. It's very unlikely.
And then 2 will be 5 over 1,000.
And then 2 would be 5 over 1,000 and so on. Does that make sense?
Yes.
So you don't have to fill it out as long as you know how to fill it out. That's really what's more important. Okay. Knowing what to do is oftentimes more important than actually doing it. Because you can always just do it later if you know how to do it. Does that make sense what I'm saying?
Yes.
Okay, so taking the time now in class to do it is just a little slightly time consuming and I want to move on because we're already behind, as long as you know how to do it. Okay, so let's look at H now in the next slide. We're still working with the same situation and we don't actually need the table because we have the dot plot as well. It's essentially the same information. It says, what is the likelihood that your class would contain 10 or more boys? 10 or more boys. So how would I do that? How would I calculate the likelihood of having 10 or more boys?
You
You do
would
it
add
the
the
same way.
number that you got
Yeah.
out of 1,000.
So tell me what numbers I'm adding. Let's go back to the dot plot and tell me what numbers.
25, 18, 5, and 1, and 0.
And then what do I do when I add them all up?
Over
Divide by
1,000.
1,000.
Over 1,000, you're done. Does that make sense?
Can you repeat that? Because I didn't hear that.
Yeah, so again, tell me what you do if you want to know the likelihood of getting 10 or more boys. Forget about what he said. Let's not just, say it again because I want to write it down. Let's do it ourselves.
I thought it would be like 10 and above, and
Okay.
those numbers, you add those and then divide it by 1,000.
That's exactly it.
Okay.
That's exactly it. Now,
10 and above. I get confused. Do we include the 10 or we start at 11?
Well-
But we include the 10.
10 or more.
Oh,
If
10
they-
or more.
Right?
Okay.
If they said more than 10,
Then you wouldn't include 10.
then you wouldn't include it. That's
right.
that's a situation of
Reading right.
reading correctly, right? Okay.
Yeah, don't rush.
So what I understand was you take 11, 51, 96, 141, 206, 27, and 18, like all.
No. Why are you doing? Why are you over there? 10 or more boys. Which is a 10 boys one?
78.
78. That's where you
Oh.
start.
78, 25, 18, 5, 1,
And 0. And you add them together and divide by 1,000, right? 10 or more boys. You look at
Okay.
the 10 through.
I get it.
So the next column, so the next question says I. It says, suppose you were actually assigned a class of 10 boys and 5 girls. Would you be justified in questioning this situation? 10 boys, 5 girls. So let's calculate the likelihood. How likely is it, based upon our graph, our data, our dot plot, how likely is it that you got precisely 10 boys and 5 girls?
78 out of 1,000.
78 out of 1,000, which is about 7.8 or about 8%. There's an 8% chance that you would get 10 boys and 5 girls. The question is something that has an 8% chance of occurring so unlikely that you would start questioning how it occurred?
For 1,000?
8%. Forget about over 1,000. We've already calculated. 7.8 over 1,000 is about 8%. Is something that happens that you get 8%, would you say, my God, that's crazy, only an 8% chance that it happens? Or would you say, okay, I didn't see it coming, but sometimes things happen like that? Which would it be? Which emotional conclusion would you make? Would you say, that's not possible? How'd that happen? Or would you say, well, didn't see that one coming, but sometimes improbable things happen?
The second one.
Okay, well, let's put it in context. You ever roll double ones? If you roll 2 dice, you ever roll double ones? You ever roll snake eyes? Yeah, anyone here, you're playing Monopoly. You ever roll double ones?
Yes.
Times, maybe. Not
Did it ever happen that you were like, double ones? That's crazy. How'd that happen?
No.
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 Okay. You know what the likelihood of rolling double ones is? It's about 3%. Okay. So if something that has a 3% chance of occurring didn't make you question it, then something that has an 8% chance of occurring should not make you question it either. Right? It's more likely than rolling double ones, and you never questioned rolling double ones before. You might have said, wow, okay, that's rare. But you don't question it when it happens. It's an unlikely event, but it's not so unlikely to say that can't be. Winning the lottery 5 times in a row, then you say, hell, winning the lottery 1 time is already saying that can't be, let alone 5 times in a row, correct? So 8% chance, okay. That was kind of weird, but let's roll with the punches. 15 boys, you start saying, okay, either it's an all-boys school, or we have the really good students, or you start asking how it happened, right? Yeah, I start asking how it happened. But 10, unlikely, but crazier things have happened. All right, so let's go to the next slide, which is slide number 9. And this is kind of like a summary of the example that we did and what we've talked about so far in this chapter. It says, if you're going to create a simulation, then the first thing you got to do is you have to model it correctly, which means if you're simulating something that has a 50% chance of occurring, then you got to make sure that whatever you're doing has a 50% chance of occurring. So flipping a coin, for example, will be a wonderful simulation for a 50% chance. Rolling a die and saying evens or odds would again be a wonderful simulation for something with a 50% chance. If I had a situation of a 1 in 3 chance, can I do that with flipping a coin? No. Can I do it with rolling a die? Yes, I just have to come up with a way of splitting the die into a 1 in 3 situation. What's one possibility for splitting a die into a 1 or 3 situation?
2?
Or 1 out of 3, huh?
1 out of 3.
Right. So if I give you a die and I say, okay, there's 6 outcomes on the die, and I want a 1 in 3 situation, how would I split up the 6 outcomes?
Roll the odd numbers? Or
Well, if I do odd or even, that's not 1 in 3. Odd or even is 50%.
I
Oh,
think in the
50%.
last class, someone said like by pairing numbers. So like 1 and 2, 3 and 4.
So tell me. So do it again. Go through it.
By like pairing numbers 1 and 2, 3 and 4, 5 and 6.
Okay.
And then that would be 1 out of third.
So
1/3.
yeah. So you can say, for example, that 1 and 2 correspond to this outcome, and 3, 4, 5, 6 correspond to the other outcome. Because 1 and 2, 3, 4, 5, 6, 1 and 3 chance. 2 out of 6 is 1 and 3. If I had cards, how could I use cards to create a 1 in 3 situation? Don't mind the guy behind the curtain. He doesn't do anything. So if I have cards, how can I use a card situation to do a 1 in 3 chance?
Last class, you said just choose 3 cards.
Just take 3 cards. Let's call it ace, 2, 3. Ace represents the thing you're looking for. 2 and 3 represent the other thing. Shuffle them, stick a card. If it's an ace, it happened. If it's a 2 or 3, it did not happen. Correct? So the first step is always to model the situation appropriately. Second step, you conduct many runs. The more runs that you do, the more accurate your outcomes are going to be. Okay? And third step is your conclusion. What is your conclusion based upon the context of the situation? I conclude that the most likely number of boys is 7 because the highest occurrence of my 1,000 runs was for 7 boys at 207 or 206, whatever it was, occurrences, something like that. That is taking your math and applying it to the context of the situation. Okay, if you just say math words, that's not in the context of the situation. It has to be specific to the situation that you're dealing with. Does that make sense? Okay, we're going to skip the next class activity. And we're going to now go to slide number 12. Okay. And slide number 12 is a situation where you where we're going to use what are called random digits to create simulations. Up until now, our simulations have been coins, have been cards, have been let's see, coins, cards, spinners, and
Dice.
right? Those have been our 4. We're now going to use what are called random digits. Now, what is a situation of random digits? It's literally just picking digits randomly. Now, human beings are not capable of picking digits randomly. If you took out a tape recorder and started recording yourself and randomly spewed out numbers between 0 and 9 for, let's say, 5 minutes, 0, 3, 2, 5, 6, 4, 1, 8, 3, 7, 9, 5, 2, without thinking, just randomly saying numbers for 5 minutes, and then actually going back over your data and checking how many times you said each number, chances are you're going to have some numbers more than others. Because you like certain numbers, you don't like other numbers. You think of certain numbers first before others, whatever the case may be. So human beings cannot create random numbers, but what can create random numbers is a computer, or at least nearly so. So a computer will create random numbers for you, or at least ones that you're justified in using. On this slide are 30 digits that have been randomly assigned. So some computer has randomly created digits. Does that make sense? With me so far? Okay.
Yeah.
What are those 30 digits? They are 0, 4, 1, 8, 1, 1, and so on. 0, 4, 8, 1, 1, 1, 7, 2, 2, 1, etc. What we need to do is use these random digits to create a scenario that has a 60% chance of occurring. Why 60%? Because let's read it. Last year, 60% of CSUN bachelor's degrees went to women. If I select 20 graduates at random, I'm curious of how many women there are. Now, I don't want to go out and actually talk to graduates because that takes a lot of time, especially during a pandemic. It's dangerous. So I'm going to simulate it. So I need something that has a 60% chance of occurring. How do I use random digits to create a 60% chance of occurring?
You have groups of 6 numbers?
So not 6 numbers. Every digit is a person. So the first digit is a person.
So every 6 digits is a person, or just
No, every digit is a person. Now, I do not know in advance what that digit is going to be. So some digits are going to represent a woman, and some digits are going to represent a man. I need to assign them in such a way that 60% of those digit possibilities would be woman, and 40% of those digit possibilities would be man. What is a good way of assigning that?
Would it be like the numbers 0 through 6 could be woman?
Okay, I love what you're thinking, but how many digits are there between 0 and 6? Count them on your fingers.
1 through 6.
Okay, fine. 1 through 6 will represent woman, and then 7, 8, 9, or 0 will represent man. Does that make sense? So then each digit represents a person, and if the digit is a 1 through a 6, it'll be a woman. And if the digit is a 7, 8, 9, or 0, it'll be a man. So based upon the data in front of us, the first person that I talked to, woman or man?
Man.
It was a man, it's a 0. Second person, woman or man?
Woman.
Woman. 4. So what I want you to do is I want you to go through 8 digits. Sorry, I apologize. 20 digits, the first 20 people. That's the whole first row and the first 5 numbers of the second row. And I want you to count how many women there were in the first 20 digits. And I'll do the same thing. Okay, I got my answer.
Said the first line, right? Both
The
lines?
first 20 digits. Remember, we're talking to 20 people. So we're not doing all 30 digits, and we're not only doing the first line. We're doing 30 digits. And the question is, in those 30 digits, sorry, why did I say 30? In those 20 digits, how many women are there?
Women are 1 through 6, men are 7 through
720.
7, 8, 9, no,
And 0.
7 and 0.
7, 8, 9, and 0.
7, 8, 9, and 0.
So of the
So
first,
there's 12 women out of those 20.
wonderful. So according to my simulation, out of the first 20 people that I talked to, 12 of them were women. Which, by the way, is amazingly exactly what I should expect if 60% are women, because 60% of 20 is 12.
Yeah,
Now, that was a coincidence. I mean, you're not always going to get exactly 12. Just don't expect it to happen. But it is the most expected value because 60% of 20 actually is 12. But does everyone see how I got 12? Is there anyone who's not sure what I'm doing or why I'm doing
you
it?
just counted to whatever the digits that were women to get 12.
Exactly. I went to the.
And then why did you say, because what did you just say about that's the most likely to get, because 12 is 60% is 12?
Because 60% of graduates are women,
Oh, that's right.
in any sample that I take, the most expected or the most likely number that I'm going to get is going to be 60%.
Oh.
So because I asked 20 women, because I asked 20 people, the most likely scenario is that 12 of them will be women. But the fact that it's the most likely does not mean it's going to happen every time.
Right. It just was a coincidence that it happened in this.
It's a coincidence. And in fact, my class yesterday, they didn't pick 1 through 6 for women. They picked 0 through 5, which is totally okay. As long as you give 6 numbers for women and 4 for men, it'll be the same thing. And I don't remember the exact number, but I do not think it was also 12. So that just happens. Okay. Of course, that was only one simulation. That was one run, correct? Like the previous example, I would then go to the next 20 numbers and do it again. Of course, I don't have 20 numbers for this page because whoever made this slide only put down 30 numbers. I would need more numbers.
What was the range again?
I'm sorry?
It was 1 to 6 for men, 7 to 0 for women?
No,
1 to 6.
This example was 1 to 6 for women and 7, 8, 9, and 0 for men.
My numbers were backwards.
I forgive you. Oh, but if you hold it up to a mirror, it should be okay.
Wise guy.
So, okay, if you didn't laugh at that, you're wrong, because that was hilarious, okay? That was on the spot funny. Okay, so if you're not laughing, you can just leave now. I don't even care. Okay. So anyway, so anyways, that was one run, and you do multiple runs, and if you have lots and lots of runs, you should get the same kind of situation that we had with the kindergartner class. Well, you can see how many times did I have 0 women? How many times did I have 1 woman? How many times did I have 2 women? All the way through 20. So your probability distribution table in that case will be 0 to 20 in your first column. And then similar to the kindergarten class, however many times it occurred over however many runs, let's say we do 1,000 again, and that would be, the second column, the same thing, right? There's a lot
Sorry, can you repeat that again? The first column, I just want to get into a pattern here.
Yeah, if you were to make a probability distribution table here,
Yeah,
what you would do again is 2 columns.
right.
The first column are all the possible outcomes, in this case, 0 through 20.
20, yeah.
For how many women there were.
Yeah.
And then the second column will be how likely each of them occurred. How do I know how likely it is? Because I take how many times it actually did occur, divide it by how many runs I made, just like we did with the kindergartner class.
Yeah.
Okay, so we don't have to do it. We know how to do it. Let's move on. Let's go to the next slide. This is slide number 13. Excuse me. So what is slide number 13 saying? Slide number 13 says, design and use a simulation to generate frequencies for compound events. A compound event is more complicated than a simple event. They call it a compound event. Let's see what this one is. If 40% of donors have type A blood, what is the probability that it will take at least 4 donors to find one with type A blood? Okay, suppose you are a hospital and you are in need of type A blood. And you know that statistically 40% of people have type A blood. Okay, but you, for whatever reason, I can't imagine why you would ask this, but suppose you're just curious, what's the likelihood? Well, here's an example. Suppose I only have 3 test tubes. So I can only test 3 people. The question is, what is the likelihood that it will take at least 4 people before I have type A blood? How likely of an occurrence is that? That's a realistic question, right? You're a hospital, you need type A blood, you only have 3 vials or 3 syringes or whatever the case may be, and you're wondering, how likely is it that I'm gonna need at least 4 people to get what I need? Because I can't, if it's 4 or more, I'm not gonna get it. Is it a 10% chance so that I can be pretty confident that I'll get my blood that I need? Or is it a 90% chance that I should be not confident that I'm gonna get what I need? That's a realistic question that you might ask. So how would I design, how would I model a situation that would work for this? How would I model a situation? I need something with a 40% chance, first of all. So can I use dice or a coin for a 40% chance? No, there's no scenario with a coin or with dice for me to get a 40% chance. Can I use a deck of cards for a 40% chance?
No, how about the random numbers thing again?
Well, we'll use that. We'll use that for sure, because that's what this section's about. But I'm just asking, could you use a deck of cards to simulate a 40% chance? And the answer is 100% yes. Just take 5 cards. 2 of them is then 40%. So I take ace 2, 3, 4, 5, ace and 2, that's type A blood. 3, 4, 5, that's not type A blood. I just constructed a 40% scenario. Can I use a spinner for 40%? Sure, just make a circle and have 40% yellow and 60% green and spin it. And if it lands in yellow, that's type A blood. If it does not land in yellow, it's type something else blood, right? You can use a spinner too. But all of those situations require you to have the apparatus in front of you. Random number generators, on the other hand, just require you to have a computer in front of you, which is a lot more likely in today's day and age. Who here has a computer in front of them? Who here has a deck of cards or a die in front of them? You do? You have a die in front of you?
And cards.
What? That's crazy talk. Well, that just defeats the whole purpose of my my simile. Simile, that's a good word. I didn't use that before. No one said anything. Simile. I'm not sure what that is, a simile, but I've heard it before and I'm going to use it. Anyways, we're going to use random number generators. I need something with a 40% chance. How can I use random digits to get a 40% chance? Give me a scenario that I can use random digits for a 40% chance.
You could do couldn't you do the exact same thing we did, except it used the male aspect of the numbers?
100%. You can rearrange them. You can rearrange them if you like, but essentially what we did before is 1 through 6 could be not type A blood, and 7, 8, 9, 0 can be type A blood.
And I'm sorry, you would do, am I getting this right? If then you'd have to do it like every 40 numbers, or how do you decide the number?
Well,
how many numbers you have to count?
Well, one second. Every digit is a person, right? Every one of these digits is a single person.
Yeah.
Okay. So if it's a 1 through 6, it is not type A blood. And if it's 7, 8, 9, 0, it is type A blood.
Oh, same.
Okay. So let's look at the random digits on the next slide. We'll use those for this particular example, not the previous slide, but we'll use those for this particular example. So the question was, what is the likelihood that it takes at least 4 people before I get a type A blood, correct? That was the question. What is the likelihood that it takes at least 4 people? Well, let's take a look. The very first digit, what is that?
3.
3, which represents what in this example?
Not.
Not. Second digit was a what?
Not.
A not. Third digit's a what?
Not.
Not. Fourth digit's a what?
Yes.
Yes. So how many people did I have to ask in this run before I got a type A blood?
Magic. 4.
4. So that means that if I make my table of possibilities of how many people I have to ask before I get type A blood, under the 4 possibility, I would make a little tally mark because it happened 1 time so far. My first run took 4 people. Agreed? Now let's do a second run. So we stopped at 8, correct?
Yeah.
So we're not going to use those 4 digits. We've already used them. So now let's move on to 4. Type A or not type A?
Not.
Not. 0.
Yes.
Yes.
Yes. So this one took 2 people before I got type A blood. So I would go to my list, and by the 2, I would make a tally mark. Oh, look at that. Who's the cutie? Ah, oh, the cutie dog. Hello. Put the dog in the front and center. Put the dog front and center. Not you, the dog. I don't want to look at you. Come on.
Wait a minute. Gallery view.
Where is the cute dog? Oh.
Oh.
Who's a good boy? Who's a good boy? Oh, the dog's gone. Anyway, so I would put a tally mark by 2 because now we had 2 people before I got someone with type A blood. Let's do a third run. Where do we leave off?
0.
0. So 1. What is that?
No.
No.
I mean, yeah. No. Yeah.
No. Next one.
No.
No.
No. No. No. No.
Wait, I thought 7's a yes.
7 is a yes. You were ahead of me.
So that one took 6 people before I got type A blood. So I would go to my table. I would put a 6 in there, and I put a little tally mark. Every one of these runs is how many people it took before I got someone with type A blood. And if I do it 1,000 times, I would do exactly the same thing, right? I would look at my table, and I would say, how many of those 1,000 times did it take at least 4 people before I got type A blood. And I would do it exactly the same way as the kindergartner class. And I would do it exactly the same way as the example that we just did with the CSUN graduates. It's exactly the same process. Does that make sense? Yes? Any questions on that, on what we're doing and how we're doing it?
What did you mean about the tally mark? So the first,
Well,
the
remember,
first
we're counting how many times each of them occurred, correct?
counting how many times you
How many-
get a,
How many times it took?
oh,
How many times it took 1 person? How many times it took 2 people? How many times it took 3 people? 4 people? 5 people?
okay.
6 people? 7 people? 8 people? 9 people?
And then back to 4 people, and it could be random. Okay.
Yeah. So after 1,000 runs, I'm gonna have all these tally marks, which I add up. This many
How
times.
many?
One.
How many times? Okay.
Yeah, makes sense. Okay. So let's skip now to slide 16. Okay. Slide 16 has a slightly more complicated scenario because now we have to construct a situation that has a 46% chance of occurring. And if I only use one random digit like we've been doing, that can be 10%, 20%, 30%, 40%, 50%, but it can't get 46%. And dice cannot get 46%. And coins cannot get 46%. And even a deck of cards cannot get 46. Well, a deck of cards actually can, although I'd have to use a lot of cards for that, 50 cards. But I can use my random digits again for 46%. The only issue here is I can't do it with 1 digit. I have to do 2 digits at a time. Every 2 digits represents a person. So I need, using 2 digits, to come up with a scenario where something has a 46% chance of occurring. What would be a scenario of 2 digits where something has a 46% chance of occurring?
I'm a little confused. How did you know you're supposed to use 2 digits instead of 1?
And do you mean like
I
2 digits as like 10, 11, 12, 13, 22,
yes,
whatever? Okay.
Yes. To answer the question, I knew it because I've done this before. And I'm trying to explain to you how to do it with the advantage that I've been there and done it. But essentially, we're starting with 0. We're starting with 1 digit, and we're just recognizing right off the bat the fact that 1 digit will not work. Because 1 digit can get 10%, 20, 30, 40, 50, 60, 70, 80, 90, but it can't get 46. So I am asking you, is there a way to use 2 digits and get 46%? And the answer is yes. Why don't we do 1 through 46 to be whatever it is in this case, type O blood, and 47 to 00, not type O blood.
Got it.
All we have to do is come up with a scenario of 46 of 100 outcomes corresponding to what we're looking for, and the other 54 corresponding to what we're not looking for. In this case, 1 through 46 out of the 1 through 00 situation is a 46% chance. Does that make sense?
Yeah, I thought you were talking about we have to do 1, 2, 3, 4. I got it.
Okay.
Thank
So
you.
does that make sense, everyone?
No, wait, 1 through 46 is 46%.
Well,
And then-
1 through 46 is how many possibilities?
How many possibilities?
That's 46 possibilities, right? 01, 02, 03, all the way through 46. That's 46 possibilities, correct?
Okay.
But how many possibilities are there for 2 digits?
91.
Not 91. How many possibilities are there for 2 digits, one after the other?
I don't understand the question.
Well, if I give you a single digit, if I give you 1 digit, how many possibilities are there for that 1 digit? What can it be? What are the possible
Got
options?
1 through 9.
No, not 1 through 9.
Those are 1 digits.
Yeah, but you're missing one.
0
Yeah, 0.
through 9.
Okay, 0 through 9. That's how many possibilities?
10.
10. And the next digit next to it, how many possibilities? 10. It's the same 0 through 9, right? So together, 2 digits back next to each other, back to back, how many possibilities are there for 2 digits in succession?
20.
You don't add them.
100?
100. 10 times 10.
Oh,
0, 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, 6, 0, 7, 0, 8, 0, 9, 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, all the way through 8, 8, 8, 9, 9, 0, 9, 1, not all the way through 9, 9. There's 100 possibilities for 2 digits back and forth, correct?
100 possibilities.
100
For 2
possibilities for 2 digits back and forth.
digits. Back and forth. Whatever that means.
Right? 100 possibilities for 2 digits back and forth. 46 of those 100 possibilities will then correspond to a 46% chance. So if I do 1 through 46, that's going to be for type B blood. And 47 through 00, that's going to be for not type B blood. So the question is, if 46% of donors have type, or it's not type B, type O blood, I'm sorry. We're looking at the first column. If 46% of donors have type O blood, what is the probability it will take at least 4 donors to find one with type O blood? It's no different than the previous example that we did.
It sounds very different.
It's not. The only difference is you group the digits by 2s instead of each one individually. So let's look at the same, let's go back a couple slides and let's look at the same random number generator. So what is the first 2-digit combo that we have in that random number generator?
31.
31. Is 31 type O or not type O?
Type
Oh.
It's type O. It took 1 person to find type O blood. My first run is over. Now, let's make a second run. What's the second number we have there?
28.
28. That's type O blood. Took 1 person again. What's the next one that I have there?
40.
40. That's type O blood. Took 1 person again. What comes next?
11.
11, then 21, then 17, then 23. Finally, I get 51. Right? 51 is the first person that's not type O blood. And in fact, either is 62, either is 52, but 17 is. So that run took 4 people. That run took 4 people to find someone with type O blood.
And it's really rare, actually.
Listen, for all I know, this scenario is completely made up. I don't know how realistic these things are. I'm not a nurse or in the medicinal field whatsoever.
But I guess that kindergarten, they're not thinking about that anyways.
And kindergartners are not thinking, it's like, oh, I'm sorry, teacher, but I believe that type O negative might be popular, but type O positive, not so much. Unless, of course, you have the correct platelets, which I mean, yeah, my guess is kindergartners are not analyzing it that deep. That's just my guess. Okay, so let's move on. So, and again, like those other situations, you would do lots and lots and lots of runs. And the more runs that you do, the more of an accurate approximation you would get for every possible possibility. You do it 1 or 2 times, it's completely random. You do 1,000 runs, and now you're getting something where it's like, okay, I see where this is going. Does that make sense? Okay, so let's skip the next couple of slides because again, we're not gonna do every single example. So let's, actually, this is, I think, where my other class ended. And I don't want the classes to be off from each other. So I'm gonna stop recording here.